Welcome to Module 1.4, where we'll explore public, private, consortium, and hybrid blockchains, as well as the layers of blockchain technology. There are several types of blockchains, each with unique characteristics, use cases, and limitations. Let's first take a look at public blockchains, the type of blockchain that forms the basis of the largest crypto networks, Bitcoin and Ethereum. Public blockchains, or permissionless blockchains, are decentralized networks that are permissionless, which means anyone can participate in the network and validate transactions. Consensus among all of the participants is achieved through various mechanisms, the most common ones being proof of work and proof of stake, as discussed in the previous module. Public blockchains offer a high degree of security, as they are supported by a large network of nodes that validate transactions. They are also transparent, as all transactions are visible to everyone, even those who don't run nodes. Public blockchains are generally censorship-resistant, meaning it can be difficult for central authorities to block or control transactions. But these strengths come with limitations. Public blockchains can be less efficient than the other blockchain types and expensive to run. For instance, proof of work and mining often require significant computational power and energy. Public blockchains face challenges with scaling and being able to change quickly due to their decentralized nature. They also lack privacy because transaction information is public and are still susceptible to attacks such as the 51% attack. Private blockchains sit on the opposite end of the spectrum. They are centralized networks limited to a specific group of participants. Private blockchains offer faster transaction speeds, greater privacy and control, but are more susceptible to a central point of failure. Because private blockchains only allow a limited number of nodes to participate, they are less transparent compared to public blockchains. Consortium blockchains, also known as federated blockchains, represent a middle ground between public and private blockchains. In a consortium blockchain, multiple pre-selected entities or organizations share the control and responsibility of maintaining the network, rather than a single entity on a private blockchain or anyone on a public blockchain. These pre-selected entities collaborate to validate transactions, create new blocks, and set consensus rules. Consortium blockchains are often used in scenarios where a degree of privacy, trust, and efficiency is required among multiple parties, such as financial institutions, supply chain management, or interorganizational processes. The benefits of consortium blockchains include reduced centralization compared to private blockchains, enhanced security and privacy compared to public blockchains, and the ability to establish tailored governance structures and consensus mechanisms to meet the specific needs of the participating organizations. Lastly, let's look at hybrid blockchains, which are designed to offer organizations the best of both worlds by running a permissioned system alongside a permissionless system. Both networks work together to control who gets to view privileged information while allowing other information to be seen publicly. There are a number of benefits to running hybrid blockchain systems that make this method attractive to organizations looking to store their data on-chain. Running a closed ecosystem means hybrid blockchains offer privacy while maintaining communication with external parties. However, running part of a blockchain privately also means the data stored on it isn't completely transparent. Now that we've taken a closer look at public, private, consortium, and hybrid blockchains, let's explore blockchain layers in greater detail. There are many ways to categorize blockchain layers. One method classifies blockchain into 5 different layers: the hardware layer, data layer, network layer, consensus layer, and application layer. These layers work in unison to ensure a blockchain operates smoothly and fulfills its intended use case. The hardware layer is made up of the computers, servers, and other hardware that run the software and store the data. This layer includes the nodes and servers run by those who participate in the blockchain, forming the physical foundation on which the blockchain operates. The data layer is where all transaction information such as transaction data, metadata, hashes, and other data is stored on the ledger. The data layer ensures that the information is stored in a secure, tamper-proof, and verifiable manner. The network layer deals with the communication between the nodes participating in the network. This layer is responsible for propagating transactions, blocks, and other information across the network to ensure that all nodes have the most up-to-date and consistent version of the blockchain. It also ensures that the nodes can communicate with each other in a secure and efficient manner. The consensus layer is the layer that is responsible for validating and agreeing on the contents of the blocks before they are added to the blockchain. This is where a blockchain's consensus mechanism sits. The application layer is where applications interact with the blockchain. It provides an interface for users to interact with the blockchain, access its data, and transact with each other. Examples of applications that may be built on top of the blockchain include cryptocurrency wallets, decentralized exchanges, and supply chain management systems. The concept of Layer 1 and Layer 2 relates to scaling solutions and is a different way to categorize blockchain layers, which we'll explore in Section 2. Congratulations on successfully completing the initial segment of our comprehensive blockchain deep dive course. In Section 2, we will explore the critical aspects and challenges associated with blockchain interoperability and scalability, further enriching your understanding of this transformative technology.